Integrated pest management has been a part of field crop production long before its formal introduction in Illinois. Some farmers have, in many cases, unknowingly practiced sound management schemes for hundreds of years. Strategies such as diverse crop rotations, early harvesting, strip cropping, mechanical cultivation, trap cropping, and manipulating planting dates are not new pest management concepts and have been relied upon by farmers for centuries. Modern farmers incorporate new scientific and technological advances such as biological control, host plant resistance, environmental information, available technologies such as global positioning systems, and transgenic crops in integrated pest management systems. The tools of a pest management program may include cultural, mechanical, physical, biological, genetic, regulatory, and chemical controls. The integration of many strategies increases successful pest control. Pest management should focus on an integrated approach that ensures various control measures. Applicators must consider the economic justification for that control. For example, we want to make sure a pest is present and causing injury before deciding to use treatment. Overuse of insecticides in field crops can lead to negative effects on non-target organisms like natural enemies or bees. Finally, we should consider the environmental impacts. Unwanted environmental hazards associated with pesticide use include pesticide residues on food products, pesticide detections in surface and groundwater supplies, and wildlife kills. The two most important tools we use to control pests are the economic threshold and the economic injury level. Looking at economic injury level, or EIL, this is the lowest pest density at which economic damage can occur. Another way of interpreting the EIL is to think of it as the level at which the cost of control measure is equal to the loss likely to be caused by the pest. Looking at the graph, we can see the number of pests on the vertical axis and the amount of time on the horizontal axis. When our pest population over time increases beyond the blue line or the economic injury level, we will not only have significant crop damage, but also economic loss. If the number of pests matches the EIL line, then we are at a break-even point and your cost of control is equal to the benefit of control. It is worthwhile to keep in mind that there are several factors that influence economic injury levels. These factors include the densities of pests or the amount of damage, the cost of treatment options, the potential value of the harvested crop, and the expected yield. Understanding these factors will allow you to make informed decisions about your field and to make more money by preventing loss. Economic thresholds, also referred to as action thresholds, is the pest density at which some control should be used to prevent a pest population from increasing further and causing economic loss. Looking at the same graph as earlier, we can see again the pest population over time and the number of pests. We've added the economic threshold line as the green line in this picture. If you apply a treatment at or just after the economic threshold, you can prevent crop loss. Economic threshold is mathematically determined densities of pests and is based on a detailed knowledge of the cost of pest control practice as well as the potential value of the harvested crop. The economic threshold can be measured as the number of insects per plant, density of weeds per foot row, number of insects per trap per week, or for diseases, since fungal pathogens are so tiny and hard to count, damage thresholds are used to determine how much damage a crop can sustain without yield loss. Damage thresholds can also be used for insect feeding. Economic thresholds may vary from the field, crop variety, and stage of crop growth and decrease as the value of the crop increases. Conversely, economic thresholds increase as the cost of control increases. Above all, the first step to determine if you've reached the economic threshold is scouting. The crop growing season is relatively short, so scouting weekly will allow you to see the changes in your pest population and make sure that the pest is in a susceptible life stage so that your treatment option will work. We will walk through the integrated pest management decision-making process. Scouting, our first and most important step, will help you decide if treatment is needed as well as whether the treatment was effective. We will start on the left-hand side of the screen by scouting our fields to see if the pest population is over the economic threshold. If it is over, we will apply a control. After that, we will scout the field again to make sure that the treatment was effective and to make sure that the pest has not returned, or that a secondary pest population hasn't grown. Now we will look toward the right-hand side of the screen, and if our pest population remains below the economic threshold, then our treatment was effective and have no need for additional treatments. As an applicator, you will continue to scout and base your treatment decisions utilizing this process. When looking for pests, we want to select scouting locations at random, then average the number of pests or the amount of damage among the plants you've selected. This prevents us from focusing on plants with obvious problems and overestimating the impacts of pests within the field. Make sure you're choosing plants at random. For example, walk a W shape within the field and collect or count pests in the 5 points. This pattern will help you to stay away from collecting only at the edge of the field, where oftentimes more insects tend to linger and not make their way into the center of the field. These pests typically don't impact the yield. If you scout consecutive plants, insects like rootworm or leafhoppers tend to fly away as you collect from the previous plant and may mistakenly be counted multiple times. Integrated pest management is far more complex than just scouting fields for pests. It's also having the knowledge of economic thresholds, pest biology, and using pesticides in a judicious fashion. A well-designed IPM program should integrate cultural, mechanical, biological, and chemical controls. The integration of these strategies increases successful pest control. Some common tactics used in cultural control include things like soil fertility, crop rotation, and choosing resistant varieties. Mechanical control options include physically removing a pest, like walking beans to remove resistant amaranthus species or water hemp. Biological control are items like releasing predatory insects, and lastly, there's chemical controls. Diving a bit deeper into IPM strategies in regards to insect pests, cultural practices are things that we can do to promote plant health. We can avoid a pest by interrupting a pest's life cycle. For example, use the fly-free wheat planting date to avoid the Hessian fly. The Hessian fly larva is pictured on the stalk on the right-hand side. Cutting alfalfa early is another cultural practice used in order to reduce the damage from the alfalfa weevil. Mechanical control strategies include tillage to destroy overwintering grasshopper eggs, or late-season weed removal to control the stalk borer. Biological or natural controls involve encouraging natural enemies or helping plants protect themselves. This includes the tenactid flies that parasitize armyworms, utilizing genetically modified corn containing Bt, and of course chemical controls. We can utilize chemical controls for rescue treatment on corn for black cutworm or banding of insecticide to control corn rootworm. Pesticides can provide effective control, but they should be used judiciously and in combination with non-chemical methods that can be incorporated into the cropping system.
Welcome to the insects section of your field crops training. In this presentation, we'll talk about common insect pests of corn, soybeans, alfalfa, and some generalist insect pests. We'll begin with corn insects. Our first insect is western corn rootworm beetle. Western corn rootworm is one of the most important pests of corn in Illinois. The larvae hatch in May and begin to feed on young corn roots. They can prune back and tunnel through portions of the roots. This leaves the plants susceptible to disease, disrupts their ability to transport nutrients, and reduces stability. When plants lose stability, they begin to lodge. Lodging means that the plants have fallen over, then begin to grow upward again, giving them a J shape at the base of the stalk. Lodging is a good indicator that rootworms are a problem in your field. Lodging can also make plants difficult or impossible to harvest normally. Sometimes rootworm adults can also cause economic damage by silk clipping. Silk clipping is when adult rootworms feed on corn silks. If large populations of rootworm adults are present, silk clipping can impact yield. Each kernel on a corn ear is pollinated individually. Each silk acts like a stamen on a flower, and a pollen grain passes through that silk for pollination to occur. So silk clipping can actually disrupt pollination and result in many immature kernels on the corn ear. The major reason people want to control rootworm adults is to prevent egg laying that could result in larval injury the following year. However, if there's a lot of silk clipping, a rescue treatment can be used to prevent further injury the same year. To monitor silk clipping by adult beetles, it's best to scout when silks are green. If you see silks clipped to within half an inch of the ear on many plants, you can apply a treatment to prevent economic loss. Usually this is a foliar spray. To determine if you need larval control the following year, scout from late July to late August using sticky traps. If you're scouting in soybeans and you find 1.5 or more beetles per unbaited sticky trap per day, you can apply a control to prevent larval injury the following spring. If you're scouting in continuous corn and you find 2 or more beetles per unbaited sticky trap per day, you can apply a control to prevent larval injury the following spring. The best way to determine the number of beetles per trap per day is to check traps weekly, then divide by the number of days since you last checked that trap. Here's an example of a sticky trap in a soybean field. Place your sticky traps at canopy level in soybeans and about ear height in corn. And here's a close-up of a sticky trap that's been in the field for about a week. If you need to treat for rootworm larvae the following year, you have 3 main options. The first is to plant a pyramided Bt hybrid. A pyramided hybrid contains 2 different Bt traits targeting rootworms. The second is to plant a non-Bt hybrid with a soil insecticide. And the third is to rotate to a different crop, because larvae can't survive on most other crops like soybeans or alfalfa. Another thing to think about is slowing insect resistance to Bt hybrids. The best way to do this is to rotate your treatment each year. If you need to use Bt corn 2 years in a row, use hybrids that express different Bt traits each year if possible. And be sure to follow the Bt refuge requirements on the label. The refuge helps ensure that insect populations in your field will be susceptible to Bt in the future. Refuge sizes might vary depending on the hybrid you choose, so it's important to check the refuge size for every hybrid. If you're not sure which Bt traits your hybrid contains, the handy Bt trait table is a great resource. It shows the hybrid name, the Bt traits in the hybrid, target pests, which herbicide resistance traits it has, and the percentage refuge required for that hybrid. You can find this as a PDF in the Additional Resources section of this training, or by clicking the link shown on the screen. Our next pest is black cutworm. The larvae are dark gray-colored caterpillars, and they grow up to 1.5 inches long. The larvae feed at night, so you may not see them in the field, but you will see their damage. When you're scouting for black cutworm, you can identify 2 signs of injury depending on the size of the larvae. Feeding by young larvae looks like small pinholes in the leaves. These are caused by larvae in their first 3 stages of growth. Older larvae can cut off young corn plants. Cutting usually occurs when larvae are nearing their full size. These larvae are large enough to wrap their bodies around the young corn plants and chew the tops all the way off. Corn is most susceptible to this type of damage in the vegetative leaf stages 1 through 4. Cutting can kill the plants or cause stunting. In this image, you can see cut and stunted plants in multiple rows. Some conditions favorable for black cutworms include crop debris left in the field, winter annual weeds in the field, and late planted corn. These are all attractive egg-laying sites for female cutworm moths. When you're managing cutworms, it's important to know that they're a sporadic pest. They don't attack the same field year after year, so it's important to scout and make sure they're present and causing injury before applying a treatment. If 3% or more of the plants are cut, you can apply a rescue treatment to prevent further loss. Because this is a sporadic pest, research has shown that preventative treatments are not effective in controlling black cutworm. In this video, we'll continue talking about corn insects. The next insect is European corn borer. Corn borer larvae have cream-colored bodies with dark spots on each segment and dark heads. There are 2 generations per year. Larvae in the first generation feed in the whorl of the corn. They chew into the leaves before they unfurl. As the leaves open up, you can see shot hole injury, which looks like lines of small holes across the leaves. Larger larvae in the first generation and all larvae in the second generation bore into corn stalks around ear level and tunnel within the stalks and ears. This can lead to stalk rot, dropped ears, or stalks that are broken off at ear level. In Illinois, broad use of Bt corn has suppressed corn borer populations to the point that they don't cause significant damage in most areas. However, it's still a good idea to keep an eye out for this pest because it has been so problematic in the past. Next is cornleaf aphid. Cornleaf aphids suck fluids from leaves and stalks of the corn plants, but most of their damage is caused by honeydew. Honeydews, they're sticky, sugary droppings that can coat leaves and tassels. Honeydew promotes sooty mold growth on leaves. Honeydew can also coat tassels and prevent them from dropping pollen properly. This can reduce pollination and result in immature kernels. Cornleaf aphids arrive in Illinois cornfields in mid to late June and are most damaging in hot, dry weather. Scout for cornleaf aphids before plants tassel. The aphids can be found on leaves, but they also hide in the whorls, so don't forget to check there. Treat for aphids when 50% of the plants, during the late whorl to early tassel stage, have 50 to 400 aphids per plant. This seems like a wide range, but it lets you bring other conditions into your decision making. We know that aphids do more damage in hot, dry conditions, so under those conditions, you can use the low number and treat when there are 50 aphids per plant. In damp conditions, treat when aphids reach the high end of that range. Next we have wireworms. Wireworm larvae are yellow to reddish brown with a hard cuticle and wire-like shape. Multiple species of click beetles can be called wireworms as larvae. They can have a 2 to 5 year life cycle depending on the species. Wireworms tunnel into seeds and seedlings below the soil level. This can cause wilted, dead, or weakened plants, which can lead to reduced stands. They are more likely to be an issue in fields rotated with small grains or sod. Next are Japanese beetles, which can injure both corn and soybeans. Japanese beetle larvae are white, C-shaped grubs with 6 jointed legs near their heads and can grow up to 1 inch long. Japanese beetle larvae chew on roots and root hairs, which can lead to irregular emergence, reduced stand, and stunting or wilting in plants. They can also cause purple coloration in the plants due to phosphorus deficiency. Other species of white grubs won't cause this kind of damage in corn. Japanese beetle adults have a metallic green head and thorax with brown to bronze wing covers, and they can be aggressive defoliators. In corn, Japanese beetles can clip silks leading to immature kernels on ears. When scouting for Japanese beetle, the economic threshold is similar to the threshold used for corn rootworms. If silks are clipped to within half an inch of the ear, you can apply a treatment. Now we'll move on to soybean insects. Previously, we covered Japanese beetles in the corn insects video, but it's important to know that Japanese beetle adults can also cause significant defoliation in soybeans. If you find defoliation over 30% or more of the leaf surface, it's time to control for Japanese beetles. Our next insect is bean leaf beetle. Bean leaf beetles can be orange, yellow, red, or even a pale gray color, with a dark triangle behind their head. They usually have spots on the center of their wing covers and stripes along the sides of their wing covers, but sometimes you can find beetles lacking spots, stripes, or both. Because of this variation, be sure to look for the dark triangle behind the head. It's always present. Bean leaf beetles can damage soybeans at different stages of growth and on different parts of the plant. During the seedling stage, the beetles feed on the cotyledons and the first true leaves, so germination is a great time to scout. If you find 16 or more beetles per foot of row, then it's time to apply a treatment. Bean leaf beetles can also cause significant defoliation on soybeans during vegetative growth. If you identify 30 to 40% defoliation during vegetative growth, you can treat for bean leaf beetles. You'll notice that this economic threshold is similar to the threshold for Japanese beetles. If you have high populations of one or both species, and you see this level of defoliation, you can treat for these beetles. If the percentage defoliation gets much higher, the plants may produce fewer pods, so this is a good time to apply a rescue treatment. Bean leaf beetles can also cause pod injury during reproductive growth. They feed on the pods but not the beans inside. Anytime a plant is wounded, the wound can be an entry point for disease, so pod feeding could also leave beans susceptible to disease. During pod fill, you can apply a control if you identify 20% defoliation or 5 to 10% injured pods. The next pest is soybean aphid. Soybean aphids are small, yellow, soft-bodied insects. They're small even for aphids, so they can sometimes be difficult to find. The best places to scout for these aphids are on the tips of stems and on the undersides of leaves. They can go through 30 generations in a year, so their populations can grow quickly. When you're scouting for aphids later in the season, they may look a little different. The aphids tend to be lighter in color. The small, shriveled white ones are actually shed skins, so they don't need to be counted when scouting. Aphids are also heavily parasitized by wasps, so you might see some large, pale aphids with openings on their backs. These are aphid mummies, and the openings are where small parasitoid wasps emerged. You also don't have to count aphid mummies while scouting, because they've already been killed. Soybean aphids are primarily a problem in the northern portion of the state, because they overwinter in buckthorn, which is common from Peoria northward. So what kind of injury can soybean aphids cause? Soybean aphids suck sap from the plants, which causes yellowing and crinkled or cupped leaves. They excrete honeydew, which supports sooty mold, and they can reduce the number of pods produced. They also have the potential to transmit plant viruses. The economic threshold for soybean aphids is based on per plant counts. Using this method, aphids are counted on 20 plants per field. If an average of 250 or more aphids per plant are found, you can apply a treatment. Scout when the plants are flowering and continue until pod fill is complete. I've included some pictures of aphids on soybean leaves to give an idea of what different numbers of aphids look like on individual leaves. These kinds of references can help you add up the number of aphids per leaf to find the total aphids per plant more quickly. Next are the spider mites. They're tiny, 8-legged insect relatives. They're so small that you'll need a hand lens to get a good look at them. One way to identify spider mites is to look for fine silk webbing running between the leaflets and petioles on plants. Spider mites do well in hot, dry weather, so they're more likely to become a problem in southern Illinois or in long stretches of hot weather. Spider mites injure plants by sucking fluids from the leaves. The mites are so small they can kill small groupings of cells, causing light-colored stippling on the leaves, which can be seen with close inspection. When identifying spider mite injury at a distance, you can see bronze leaves, curled leaves, leaves dropping off the plants, and stunted plants. With enough injury, this can result in yield reduction. Now we'll move on to alfalfa insects. We'll start with alfalfa weevils. Alfalfa weevil larvae grow up to about half an inch long. They are green with a white stripe down their back and a dark head. The larvae skeletonize leaves. As they feed, they strip away the green portions of the leaves, which can give the field a frosted look. Alfalfa weevil adults are a quarter of an inch long. They are a medium brown color with a dark brown stripe down their back. Like all weevils, they have a strong snout-like appearance and have hard wing covers that make them difficult to squish. Adults chew stems and leaves, causing them to have a feathered appearance. Scout for alfalfa weevil after each alfalfa cutting because this is when insect injury is most likely to occur. There are different economic thresholds for different cuttings. After the first cutting, if you find 3 or more larvae per stem and 20% or more of the tips skeletonized, you can apply a treatment. After all later cuttings, if there is feeding on 50% of the crowns and no regrowth for 3 to 6 days, you can apply a treatment. Next we have potato leafhopper. Potato leafhopper adults are 1/8 of an inch long with green, wedge-shaped bodies. This species causes injury by sucking fluids from leaves. Potato leafhopper feeding can cause yellow leaflets, leaflet curling, and dark brown leaflet tips. Scout for potato leafhoppers after the first cutting when the alfalfa is susceptible to injury, and continue scouting after each subsequent cutting. In this video, we'll cover a couple of generalist insect pests. First we have armyworms. Armyworm larvae have green to brown bodies with an orange stripe down each side. They can grow up to 1.5 inches long. Armyworm larvae feed in groups at night or on cloudy days, so you may not see the insects in the field, but you will see their damage. The larvae damage plants by feeding on leaf edges. When they feed on wheat, they can also chew through stems, causing wheat heads to fall off. While armyworms can cause significant injury, populations are usually controlled naturally by tachinid flies. Our last insects are the grasshoppers. Grasshoppers feed on corn, alfalfa, soybeans, and small grains. In most cases, grasshoppers are only an issue along the edges of fields and don't cause significant injury. In warm, humid weather, the nymphs are prone to disease, which can prevent populations from building up. Grasshoppers lay their eggs in the soil, so they can be more of a problem in no-till fields. There are different economic thresholds for grasshoppers depending on their location. In non-crop areas, 15 to 20 nymphs per square yard can warrant treatment. In cornfields, 7 or more adults per square yard can warrant treatment. And in soybean fields, 5 to 10% injured pods can warrant treatment. This is the same economic threshold for pod feeding that we saw with bean leaf beetles.
Welcome to the Field Crops Weeds section. We will cover scouting, weed ID, why weed control is necessary, herbicide application timings, factors that affect rate and carryover, environmental effects, adjuvants, drift, dicamba, acid equivalents, herbicide mode of action and injury symptoms, conservation tillage effects on weed populations, and resistance. That's a lot to cover, so let's get started. Good weed control begins with proper identification, or ID, which begins with scouting. When should you scout for weeds? It depends on the situation and what you want to achieve. To prepare for post-emergent applications, scout early to see what's germinating. To differentiate among species of amaranthus or pigweeds, wait until the flowers develop to make the task easier. However, if Palmer amaranth is suspected, it should be identified as early as possible due to its quick growth rate. Scouting can be used anytime to look for new species. Lastly, late-season windshield surveys can help determine what was not controlled by the current season's program and plan better for next year. Heavy lamb's quarters pressure at the end of the season can signal that a pre-emergent herbicide could be a nice addition the following year. For University of Illinois control recommendations, consult the bulletin. If all weeds would emerge at the same time, control would be much easier. Different weeds can emerge at different times of the year, thus making control challenging. Kochia and prostrate knotweed emerge very early in the spring. Hop-horn beam copperleaf can emerge in late July, and rarely do we see it emerge before late May or early June. Few, if any, herbicides are able to provide sufficient soil residual activity to control the latest emergence event of this weed. We can categorize weeds based on their beginning germination timing, which stays fairly constant from year to year. Iowa State University's Weed Emergence Sequences poster can help you know when to scout and when to apply controls. Proper identification is important. If we believe we have one species, but in reality we have another, we may be using improper control tactics. This picture reminds us that two species may look very similar and may be easily confused. When we look closer, we see that the leaf serration is more coarse on the left and more finely toothed on the right. The plant on the left is prickly sida, and the plant on the right is hop-horn beam copperleaf, which is a newer problem across Illinois that can be challenging. It is a type of spurge, but does not have the characteristic sap of spurges. As these two seedlings develop further, they will be much easier to tell apart. Again, proper identification is crucial to good weed control. You should be able to easily recognize the primary weed species in your area, and sometimes mystery weeds appear when an unrecognized species moves into an area. It's helpful to know the basics of weed identification and what plant structures to focus on. Grasses can be particularly challenging. The differences are subtle, and a magnifier and good lighting may be needed to see the structures. The leaf sheath wraps around the stem. It may be closed or split, round, like many of our grasses, or flattened, like barnyard grass, for example. And finally, smooth or hairy. Large crabgrass has a hairy sheath, and quackgrass can be very hairy when young. For the purposes of preparing for this test, it's not important to memorize what species has what characteristics. However, it is important to know there are differences and what to look for. On the leaf blade, look for hairs on the top and on the bottom. This could be helpful in differentiating among species of foxtail. With post-emergent herbicides, sometimes the level of control is dependent on foxtail type. ID is important. Green foxtail has no hairs on the leaf surface, while giant foxtail is hairy, and yellow foxtail has long, scraggly hairs at the base. The ligule is an extension of the sheath at its intersection with the blade. Many weed ID keys will begin with the ligule. The ligule can be membranous, as shown in the illustration. It will be one solid piece that is translucent. It can be tall or short. Johnson grass, shattercane, and quackgrass all have membranous ligules. The ligule may be hairy with a line of hairs. Again, either short or tall. The foxtails and panicums have hairy ligules. Finally, the ligule may be absent and simply not there at all. This is the case with barnyard grass, and it is a key identifying feature for this plant. Auricles are projections of the blade that extend around the shoot at the collar. While absent on most weedy grasses, one species commonly found in field crops that has prominent auricles is quackgrass. The auricles typically clasp the stem. This is a key identifying feature of quackgrass. Sedges are grass-like with triangular stems. The leaf blades are waxy. Sedges can spread by seed, but also by rhizomes and tubers, commonly referred to as nutlets. Again, ID is important for control. Herbicides selective for controlling grasses will not control sedges. Broadleaves are generally easier to identify than grasses due to the structural differences among species being greater and more obvious. Cotyledons may or may not be present, but they are always oppositely arranged. True leaves are produced after the cotyledons and may be a different shape than the cotyledons. The leaves of this velvet leaf plant are heart-shaped, softly hairy, large, and have a distinct odor. The arrangement of the true leaves can be alternate, opposite, or whorled. The leaves of this velvet leaf plant are alternate on the stem. Leaf petioles attach the leaf to the stem and vary in length, color, and hairiness. With common cocklebur, the cotyledons and first pair of true leaves are opposite, while the subsequent leaves are alternate. The leaves are ovately shaped and rough textured. The margins are toothed with rounded tips. The petioles are long, rough, and purple. Many good weed ID books and apps are available. For weed ID assistance, contact your local extension office or the University of Illinois Plant Clinic. While preparing for the General Standards test, you learned about different life cycles of weeds. To build from there, we'll talk about perennial weeds in more depth. Perennials can live for many years. They can spread by seed and by vegetative propagules such as rhizomes, which are lateral underground stems distinguished by nodes and scale leaves. Rhizomes can be found on Johnson grass, quackgrass, and yellow nutsedge, to name a few. They can grow several feet long. Budding roots are roots that function in food storage and reproduction by producing shoots. They typically grow deeper than rhizomes. Budding roots are also known as creeping roots and are sometimes called rhizomes, too, by weed scientists. Do not stress over the different terminology. The primary thing to know is that their presence can make complete removal of a certain weed species like hemp dogbane or Canada thistle more challenging. Tubers are thickened underground stems with buds. Nutsedge tubers are often called nutlets. These can remain dormant in the soil for 10 years, simply waiting for conditions to be perfect to produce shoots. Bulbs are underground storage structures with a short stem and fleshy leaves. Examples include wild garlic, wild onion, and Star of Bethlehem. Vegetative propagules allow overwintering and can be produced in as little as 4 to 6 weeks after germination. After that time, top growth can be destroyed and new growth will rise up from the stored food reserves in these structures. Control tactics may need to be repeated with perennial weeds, and systemic herbicides are recommended. In short, weed pressure can reduce yields and make harvest difficult. Weeds affect crop production by competing with crops for light, nutrients, moisture, and space. Weeds that emerge before full crop canopy are the most competitive. In soybeans, heavy infestations of black nightshade berries have resulted in dockages at the elevator. Vines such as morning glory or burnt cucumber can entangle and lodge plants. Heavy grass pressure slows down harvest of soybeans. Additionally, importing countries may reject or destroy incoming grain that has too many weed seeds. Thanks to WSSA and USDA's Clean Bean Initiative, efforts are being done to protect exports. Much of their recommendations focus on changing up management practices to avoid development of resistant weeds. More information can be found on USDA's website. Search for the Systems Approach for U.S. Soybeans. Let's talk about herbicides in general. Cultural and mechanical practices alone often do not give adequate weed control, so herbicides are commonly used in most of the row crop acreage in Illinois. It is important that the applicator understand the principles of weed control when using herbicides. Several acronyms are used to describe the application timings of herbicides. Here's a brief review. EPP stands for early pre-plant. These can be applied several weeks before planting. PPI stands for pre-plant incorporated. These must be mechanically incorporated into the soil by tillage. These applications were once very common but have declined in recent years with the adoption of conservation tillage systems. Pre can stand for either pre-plant or pre-emergence. Pre-plant means it's applied prior to crop planting. Pre-emergence means it's applied soon after planting, but before emergence of the crop and weeds. As soon as these herbicides are applied to the soil, they start to degrade. Those applied close to planting usually have better performance, but they do need rainfall to work. Finally, post stands for post-emergence. These applications are made after the crop and weeds have emerged. So when should weeds be controlled so that crop yield is not reduced? Most Illinois row crop weeds should be controlled within 4 to 6 weeks after crop emergence. More specifically, in corn, control weeds before they reach 3 inches in height. In soybean, control weeds before they exceed 6 inches in height. Palmer amaranth is the exception to this rule and should be controlled before exceeding 3 inches. Note that the timing is earlier for corn, as seedling corn is less competitive and yield loss occurs sooner than in soybean. Also note that weed size is not a hard number, as several factors can influence when weed competition will start reducing yields. Factors such as weed pressure, date of planting, early season growing conditions, etc. If weed pressure is heavy, weed control timing based on weed size becomes more important than if weed pressure is average. Plus, an advantage to controlling weeds when they are small is that they are much easier to control when young. And finally, early applications allow time for Plan B should resistant populations present themselves. When are weeds the most susceptible to herbicides applied post-emergence? Regardless of life cycle, weeds are most easily controlled in the seedling stage. There are no stored food reserves. The leaf surface will have fewer hairs and less wax than when mature. For all life cycles, the best time to apply post-herbicides is when the weeds are young and actively growing. Annuals become progressively more tolerant to herbicides as they mature. Biennial weeds are also very susceptible when in the rosette stage. Good times to apply would be in the first year before frost or in the second year before it bolts. For perennials, there are 2 good times for applications, in the bud to bloom stage and also in the fall, just prior to dormancy. Systemic herbicides applied during these times are carried more easily to the roots. Again, the best control is achieved when weeds are in the seedling stage. Soil-applied herbicides are an important part of weed control programs. Their effectiveness is influenced by factors such as soil texture and organic matter. The uptake of soil-applied herbicides by weed seedlings requires that the herbicide be dissolved in the soil water or be in a vapor phase. Therefore, these herbicides must be moved into the soil by mechanical methods or by precipitation, typically a half to 1 inch of rain. In drought years, these products can fail. To maximize effectiveness, the herbicide must be where the weed seeds are, and most weed seeds germinate in the upper 2 inches of the soil. Of those listed here, most germinate in less than 1 inch deep. When left on the soil surface, certain herbicides can degrade easily. If placed too deeply, weed germination will not be prevented. Several factors influence the activity or level of control you get with soil-applied herbicides. These factors affect the application rate too. Adsorptivity, the ability of soil to bind pesticide molecules, depends on soil texture, the percentage of sand, silt, and clay. Therefore, a range of rate recommendations is provided on the label of many soil-applied herbicides, and sometimes certain products cannot be used on coarse soils low in organic matter. To simplify our discussion, this material is in a table where you can see how certain conditions would result in a higher or lower application rate being needed. Higher rates tend to be required with soils that are high in either clay, organic matter, or crop residue as soil cover. In contrast, lower rates tend to be required with soils that are sandy, low in organic matter, and without much crop residue as soil cover. Reduced tillage systems may require higher rates, as organic matter can tie up soil-applied herbicides, leaving less available for weeds to take up. Therefore, a higher rate may be needed to account for this. Finally, applying a product in a tank mix may allow for reduced application rates compared to applying as a standalone product. You can also get increased control overall with tank mixing. When rates are too high, or when environmental conditions are such that the herbicide does not break down in a timely fashion, succeeding crops can be injured. This is called herbicide carryover. Here again, we'll use a table to discuss the factors that influence carryover. Carryover potential is high when herbicide persistence is long, when application timing is late, when precipitation is low, when temperatures are cool, and when the rotational crop time is short. In contrast, carryover potential is low when herbicide persistence is short, when application timing is early, when the amount of precipitation is high, when temperatures are warm, and when the rotational crop time is long. This is carryover injury on corn from Scepter or Imazaquin that occurred after the 1988 drought. Imidazolinone and sulfonylurea herbicides can cause bottlebrush roots. Typically, herbicides break down in a timely fashion. Degradation will occur more quickly in warm, wet conditions where soil microbes are actively feeding and chemical reactions can occur more quickly. It's the colder, drier years that lead to carryover problems. No one can control the weather, but applicators can control rates and timings, and producers can control planting dates. This is carryover injury on corn from Fameciphin or Flexstar. Late season applications on soybean, followed by dry conditions and early planting, resulted in striped leaves. There's a 10-month rotation interval on the label. Reading and following labels can prevent injury. It's common to mix 2 or more herbicides in the tank. Combinations provide benefits such as controlling additional weed species. A grass product may be mixed with a broadleaf product. Atrazine is often added to soil-applied grass products such as metolachlor or acetochlor. Sometimes mixing allows for less of a persistent product to reduce the risk of carryover. Combinations can minimize potential for resistance to develop, or if resistance is suspected, a combination can help ensure control. When using combinations, ask yourself, is each product labeled for the intended use? Is the combination labeled for use? If not, you are liable. Certain products may not mix well together or may result in antagonism when combined. The risk falls on you as the applicator. Are the rate and timing correct for each product? Are all restrictions being followed? For example, glyphosate can be applied on corn up to 30 inches tall, but when tank mixed with harness, the maximum height is reduced to 11 inches. All product labels being used must be read in their entirety. We'll turn our focus now to post-emergent herbicides. Because these are foliar applied, interactions with soil texture and organic matter are minimized, but interactions with prevailing environmental conditions are often magnified. Post-herbicides are often the best choice for controlling perennial weeds like pokeweed, late germinating species like morning glory, and volunteer corn. Just as there are important factors in determining application rates for soil-applied herbicides, there are factors to consider when choosing post-herbicide rates. Of course, the herbicide must contact the plant, absorb through the tissue, move to the site of action, and induce some phytotoxic response. Much can go wrong. The label may list a range of rates. In general, the higher end of that range would be used if weed size was large, weed density was high, the product was a standalone product without an adjuvant, and environmental conditions were cool and dry. In contrast, the lower end of that range would be used if weed size was small, weed density was low, the product was tank mixed with other products or used with an adjuvant, and environmental conditions were warm and humid, which promotes plant growth. Tank mixing can result in lower use rates. However, if resistance is suspected, the full rate should be used. Most labels provide guidance on rates. Never exceed the labeled rate. Adjuvants are often added to post-herbicides to increase effectiveness. Non-ionic surfactants increase spray coverage by decreasing the surface tension of water, so more herbicide is absorbed. This allows droplets to spread out rather than bead up like water droplets will do on a freshly waxed car or on a waxy leaf surface. Crop oil concentrates help to spread the herbicide and keep the surface moist. Oils increase penetration into the cuticle. Ammonium fertilizers are added to increase control of certain weeds, such as velvet leaf, and to help reduce the effects of hard water with glyphosate. The environment greatly affects how well post-emergent herbicides are absorbed, which in turn affects activity or control. High herbicide activity can be found when there is good soil moisture, yet no rainfall occurs too soon to wash the application off. This allows the product time to be absorbed, typically 2 to 6 hours. High activity is achieved with hot, humid weather when there is increased absorption. Rainfall too soon can result in low activity, as can insufficient rainfall. During times of drought, translocation within the plant will slow as the plant conserves water. This is bad for weed control. Avoid applications to drought-stressed plants. Also, when temperatures are too cool, plant growth will slow, causing the herbicide to sit in the plant, which delays injury symptoms and control. Drift can occur as particle drift or vapor drift. Complaints associated with glyphosate and paraquat are common simply because these herbicides are non-selective and used on many acres. Remember that all herbicides are subject to particle drift. With vapor drift, some formulations volatilize more readily at lower temperatures than others, such as ester formulations of 2,4-D and older formulations of dicamba. However, even newer formulations of dicamba now have required temperature restrictions to help prevent vapor drift. The original formulation of clomazone could volatilize when left on the surface of moist soil, and many trees were bleached white as a result. A formulation change resulted. With the widespread planting of dicamba-tolerant soybeans came widespread use of dicamba and record-breaking reports of injury to non-target plant species. Several factors contributed, including the use of non-approved formulations, temperature inversions, not reading and following label directions, particle drift, etc. Additional restrictions were put into place to reduce off-target movement, but the additional restrictions did not prevent injury to non-target plants. The 3 approved products have experienced various label cancellations and reintroduction to the market. At the time of this recording, it is unknown if dicamba will again be labeled for in-crop use in Illinois soybean. But labels with new restrictions and endangered species protection language are being considered. Also, it is likely that if these products receive federal approvals, that additional state restrictions will again be implemented. For up-to-date information concerning dicamba use in Illinois, consult the Illinois Department of Agriculture's website. Applicators must remain diligent in their stewardship efforts to keep this viable weed control tool. All restrictions and mitigations must be followed. With increased public awareness, reports of injured trees, and calls for dicamba to be banned, this is especially important. In recent years, the use of these products in crop has included several restrictions that must be followed. Applicators must use only formulations approved for this use pattern. Applicators must consider the potential for drift to surrounding sensitive areas. New low volatile formulations are still capable of causing off-target damage. Time of day must be considered to avoid temperature inversions. Applicators must survey neighboring fields or consult with the sensitive crop registry. Applications cannot occur after a state-mandated calendar deadline and cannot be made if air temperatures, forecasted or actual, exceed a state-mandated threshold. They must have the required annual auxin-specific training, which is separate from this training. For more information, consult the Illinois Fertilizer and Chemical Association's website. Individuals who handle and apply these formulations must be a certified applicator, as these formulations are restricted use pesticides. This is achieved by successfully passing the field crops exam and applying for licensure. And finally, they must carefully read and follow all label directions, including many restrictions and limitations not typically found on other labels, such as a maximum application speed, buffers, an extensive tank clean-out procedure, and a very detailed record-keeping requirement. In short, if you are not committed to reading and following the labels and all included restrictions for these products, you should not be using them. There can be other differences in formulations. If the active ingredient has been derived from a parent acid, which is the case with glyphosate and 2,4-D, you'll need to look at the amount of acid equivalent, or AE, in the product. When comparing two products, true equivalents are based on AE, not AI, or active ingredient. To simplify this complex topic, acids make poor herbicides. To improve solubility or absorption, the manufacturer will convert a parent acid to an ester, salt, or amine. This conversion adds weight, which then increases the AI amount given on the label. That makes comparing products simply by AI very misleading. To accurately compare formulations, the AE must be used. Keep in mind, both AE and AI may be presented on one label. Herbicide applicators should understand basic concepts of mode of action and injury symptoms. This knowledge can help you determine if your herbicide is working or if drift injury has occurred to non-target plants. Note that injury symptoms will be very similar for treated weeds or non-target plants. We'll go through some of the main herbicide families and prepare you for knowing the typical injury symptoms shown and how each moves within the plant, if it moves. Two terms describe how and where herbicides work. The mode of action, or MOA, describes how the herbicide inhibits plant growth to cause death. The site of action, or SOA, determines the exact location within the plant where the herbicide acts. Confusing the terms is not important if you are grouping herbicides by injury symptoms, but if you are trying to reduce herbicide resistance potential, or if you are managing resistant biotypes in the field already, focusing on the SOA will result in more control options. Look for the numbering system on labels to make resistance management easier. Photosynthetic inhibitors inhibit photosynthesis. Several are primarily soil-applied, and they translocate in the transpiration stream, so the xylem or water stream, from the roots to the transpiring older leaves. Symptoms slowly appear on the oldest growth first. Yellowing, called chlorosis, occurs first in the transpiring older leaves. Death, called necrosis, follows. The yellowing will occur between the veins in herbaceous plants and in the veins in woody plants. When photosynthetic inhibitors are foliar applied, rapid wilting and desiccation occurs. Meristematic inhibitors primarily affect the growing points, called meristems. Products can be foliar applied, soil applied, or both. Glyphosate is a foliar-applied meristematic inhibitor that causes very slow chlorosis followed by necrosis. Grasses will show stunting and narrow upright leaves. The chlorosis of glyphosate may appear almost white or light green. Soil-applied meristematic inhibitors affect developing seedlings. There are two types. Root inhibitors, like the dinitroanilins, inhibit root growth, which blocks the uptake of nutrients and water. Surface applications can result in calluses, stem breakage, and lodging. Broadleaf plants will show swollen hypocotyls and crinkled leaves. Shoot inhibitors cause shoot deformities. Chlorosetamides and thiocarbamates applied to grasses will cause onion leafing or leafing out underground. The corn pictured here has failed to unfurl its leaves. This can occur if corn is planted too shallowly or if conditions are cool and wet. On broadleaf plants, we see leaf malformations. Some meristematic inhibitors are both soil and foliar applied. The imidazolinones and sulfonylureas are commonly referred to as ALS inhibitors. Symptoms include stunting or shortened corn internodes. Death is slow. Grasses typically show purpling on new leaves and pruning, known as bottle brushing, on roots. Broadleaves show yellowing at the leaf margins, and the veins can turn light yellow to purple. Growth hormone herbicides mimic growth-regulating compounds. Generally, these are foliar applied and translocated in the food stream or phloem from the food-making older leaves to the new growing tissue that needs the food. These affect the newest plant growth first, resulting in a variety of symptoms like leaf rolling, epinasty, which is stem or petiole twisting, strapped or cupped leaves, callus tissue, stalk brittleness, fused brace roots, and malformed roots if soil applied. Many vegetables and ornamentals are very sensitive to very small amounts of the growth hormone herbicides. Contact herbicides are foliar applied and require good coverage as they do not translocate. They rupture the cell membrane, causing direct cell necrosis and rapid tissue death. These are used as defoliants and desiccants, typically with surfactant or crop oil concentrate. Often they are non-selective. For more information about mode of action and injury symptoms, consult with the Field Crops Training Manual. Additionally, the Field Guide to Herbicide Injury on Landscape Plants can assist with diagnosis of possible drift. Weed control and conservation tillage require special considerations. Reduced tillage can result in increased weed numbers and domination by different species than those found in conventional tillage systems. Weed populations can be affected by conservation tillage. Weeds that germinate on or near the soil surface can become more prevalent because seeds aren't being buried by tillage. You may see an increase in grasses, volunteer corn, and small-seeded broadleaves, including water hemp and lamb's quarters. You may see a decrease in larger, deeper, germinating summer annuals. Weed roots are disturbed less, making biennial and perennial weeds more of a problem. And finally, winter annuals benefit from no fall tillage as there is little disturbance. Some considerations for conservation tillage systems include the following. Higher rates may be needed depending on increased weed populations and increased crop residue. Even distribution of soil-applied herbicides can be challenging. Cover crops may need to be killed. Non-selective foliar herbicides are commonly used for burn down of cover crops, grass, and early emerging weeds. Paraquat, glufosinate, and glyphosate are commonly used, but 2,4-D and dicamba may be used as well. Herbicide-resistant weeds are an ongoing struggle for applicators and producers. A resistant plant is a member of a species that, as a whole, is susceptible to the herbicide. The resistant plant is a biotype of that species that is no longer susceptible to the herbicide. According to the Weed Science Society of America, when a single herbicide is used repeatedly to the exclusion of other controls, weeds can become resistant and can grow unchecked. Billions in potential economic losses can occur from uncontrolled weeds. Therefore, preventing resistance is imperative. Slow the evolution of herbicide-resistant weeds by scouting regularly to identify resistant weeds or any populations not being controlled. Because resistance thrives when using the same site of action repeatedly, rotate herbicides with different sites of action. Apply tank-mixed, pre-packaged, or sequential mixtures, including pre-emergent herbicides with multiple sites of action. Control escapes so that seed spread is halted. Use mechanical controls, cultivate, or hire bean walkers. A way to control weed seeds at harvest is the Harrington seed destructor, which crushes weed seed into a fine powder to prevent germination. Less expensive adapter kits for combines may be available. This works well on water hemp And newer research on this weed shows that something other than herbicide rotation must be used to ensure that no seed are produced. And finally, to further avoid spread, be sure to clean any tillage or harvest equipment after working in fields with resistant weeds. Suspected areas could be harvested last or even skipped altogether.
While specific details found in this section are somewhat technical and not required knowledge for the test, this information can be beneficial to field crop applicators. Users of paraquat should be aware of changes regarding use, which will be phased in with new product labels. Due to a high number of accidental deaths, with many being from beverage container storage, only certified applicators who complete an EPA-approved paraquat training program every 3 years will be able to apply paraquat. Also, direct supervision of uncertified applicators will not be allowed, and closed system packaging will be required for all non-bulk containers less than 120 gallons. Paraquat was already a restricted use pesticide due to toxicity concerns. With no antidote, one small accidental sip can be fatal. Listed are the known herbicide-resistant weed species in Illinois. At this recording, we have 12 species with 8 sites of action. We know that one or more can occur in a field or in one plant. Unfortunately, we have no reason to think the list will stop growing with a lack of development of herbicides of novel sites of action. In 2016, the PPO inhibitors were added to Palmer amaranth, and auxins, specifically 2,4-D, was added to water hemp. In 2019, the VLCFAs were added to water hemp. This stands for very long-chain fatty acids, which is better known as the group 15 herbicides, or chlorosetamides, with the highest resistance ratio with S-metolachlor, but resistance is to all group 15 products. This was the first worldwide occurrence in a broadleaf, and we are now finding issues with this statewide. This resistance is metabolic. Some types of resistance are caused by a change in the herbicide target site that does not allow the herbicide to bind. But group 15 resistance occurs via rapid herbicide metabolism. Enzymes break down the active ingredient very quickly and before it can cause its normal lethal effect. This could provide cross-resistance to multiple herbicide groups, even new herbicides never before applied. However, these herbicides remain important weed management tools, and this reminds us that herbicide stewardship is as important as herbicide trait selection. It's critical to determine alternative controls to supplement herbicides. In recent years, we've been concerned about glyphosate-resistant water hemp, which we likely have in every county by now. We have particular concerns about resistance to groups 4, 15, and 27, and now more recent concerns with glufosinate group 10. With multiple resistances occurring in the field or even in individual plants, it has been very difficult to manage with post-emergent herbicides alone. Rotation buys time, but more must be done to ensure no seed are produced. There exists an urgent need for integrated weed management programs that return zero seed to the soil seed bank. If uncertain about the identification of a mysterious weed, or perhaps the species of amaranth, the University of Illinois Plant Clinic will accept plant tissue or seed samples for identification. The plant clinic can also screen Amaranthus species for glyphosate and PPO inhibitor resistance. Contact them for more information. The Weed Control Guide has herbicide recommendations for field crops and pastures and is a collaborative effort created by weed specialists at University of Illinois, Purdue University, The Ohio State University, and University of Missouri. The herbicide classification chart can be useful in planning management programs. This chart groups and color codes herbicides by site of action to assist with selecting and rotating herbicides to delay the development of herbicide resistance. This chart, along with other resistance management resources, are available courtesy of the United Soybean Board and industry partners at iwilltakeaction.com. The University of Illinois Regional Agronomy Summits are in-depth programs providing university research-based information on current crop production issues. Certified crop advisors may earn CEU credits. For more information and to register, check out the website listed.